So we've learned that if we want to deal with more than one body in quantum mechanics, then the entire system is described by the tensor product of the two Hilbert spaces. In other words, if you have one system that's an element of one Hilbert space, and another system that's an element of a different Hilbert space, then the total system, whenever you're describing these two things together, you need to work in the tensor product space of the two Hilbert spaces. Now the fastest way to get a handle on the tensor product space is to look at the basis for it. So if I have a Hilbert space H1 and has a basis, and my other Hilbert space has another basis. Now these two things don't have to be the same dimension. These could be very different. This index here might be a composite index. It might be discrete, continuous, or both. That's fine. These can be very different. But if we have a set of basis states here and a set of basis states there, then the set of basis states for the tensor product is simply. And just by inspection, we see that we have all the indices from the first Hilbert space and all the indices from the second Hilbert space. And so what we've done is we've added a dimension. All the dimensionality of the first Hilbert space has been added to all the dimensionality of the second Hilbert space, and so we've got a much bigger object here. And that means that a general state for the combined system has a coefficient for every different combination of j's and k's. Now, if these two states were separable, in other words, if we could always say that the state of the first Hilbert space and the state of the second Hilbert space didn't affect each other, then these coefficients here would have to be separable, but in general they're not. And we can see the linearity of the system. Supposing we started with psi1, which we could expand in terms of the basis, and we also expanded phi1 in terms of its basis, then the tensor product of these two things, because the tensor product is completely linear in both arguments, we can take out the sums and take out the coefficients, and we just get a double sum. And you can see what I mean by these coefficients CJK being separable if our initial state was separable like that. Now writing out UJ cross VK is kind of tedious after a while, and so we have various kinds of shorthand for that. I'll show you those. So just sticking them together like that works just as well. We know that's not an inner product because it's not a bra ket, it's two kets stuck together. And sometimes we get bored with all this material in the middle here, so we make it even more compact, and we just stick the indices together. A general operator on this combined Hilbert space might look something like this. It's always easy to get a general operator if you have a general basis. You just need a bra and a ket for each of the basis states. And if we'd had operators on our previous Hilbert spaces, then the tensor product of these two also follow the normal rules of linearity, where again we see that instead of having a coefficient for every single combination of indices in our combined system, which we have in the general operator case, we have coefficients that separate into functions that only depend on the indices that affect each system. So this is system 1 for Hilbert space 1, and the J and L are the indices for the basis states in that space, and this is system 2, and the K and the M are basis states for elements of the second system. And that separability for the operators is exactly the same as the separability for the states, if indeed the system is separable. But again, we have cases where there are operators of great interest where the operators are not separable. An example of that would be some kind of observable where we were genuinely looking for some kind of correlation between the two systems. Now, Feynman once said that practically everything that's interesting in quantum mechanics and strange about quantum mechanics can be discussed in terms of a simple two-slit experiment. So let's try and talk about many-body quantum mechanics in terms of a two-slit experiment. So there we have two slits, and what we're going to have is we're going to have a wave coming from this side, described by a wave function. It's going to come through these slits, and of course it's going to spread out from the slits, and then we're going to get an interference pattern. And this interference pattern we're going to detect on a screen. Now, quantum mechanically, when we look at the screen, the object that's described by this wave function goes through those slits, forms an interference pattern, and then appears. And the measurement process means that it'll appear randomly in a single position somewhere on that screen. And so we get just a single blob. But over time, if we do this experiment many times, statistically, we see that interference pattern in the appearance of that blob. And so it's appearing. And it looks a lot like a single particle that's traveling some kind of classical trajectory. But of course, if we cover up one of those slits, then we never see that interference pattern. And if we cover up the other slit, we never see the interference pattern. So it's only when both slits are open at the same time that we see the interference pattern. And so that blob is definitely aware that both slits are open. And so we ascribe some kind of reality to the wave function, and that's the theory of quantum mechanics. But we don't have to actually cover up a slit to have that happen. All we really need to do is we need to know which slit the object went through. Because if we measure the wave function back there, then the wave function should collapse back there. And the simplest possible system we could put in to try and measure this would be a simple yes-no system, something with two states, like a two-level atom or a spin-half particle. So let's put this on a more mathematical footing and write down the wave function where it's gone through one of the slits. And because it's got some spatial structure here, I'll just write it in terms of a spatial wave function, just in one dimension. And here's my basis set, the position basis. Now it could go through there, or it could go through the lower one. And so these two wave functions are just the coefficients of the particle when it goes through the top or the bottom slit, respectively. Now if we measure what happens at this screen, if we measure this purple wave function at this screen, then the wave function will collapse and will either go through the upper or lower slit. And if it does that, then there will be no interference pattern on the screen. But if instead of that, instead of making a measurement, we just make a softer assumption and we assume that we're simply going to interact with this blue two-level system. And if the particle goes through the lower slit, then it's going to change the state of this two-level system. My question is, what are we going to see on the screen?